Here's an introduction to star formation to accompany Chapter 21 of the textbook Astronomy from Open Stax. So here we're talking not just about stars, but about stellar systems in general, because as we'll go into in the next lecture, this is also kind of the beginning of planet formation as well. So a stellar system, what do I mean by that? Is I mean you have a star or stars and a planet or planets. So, this is an artist's conception. If you were to look out in the sky, you'd see that most stars that we know of have planets, or we suspect they do. They can be hard to detect. And you can also have double star systems and whatnot. But in general, if you look out in space, each of the little stars that you see in the night sky, a lot of those probably have a planet or several planets around them. So what is a planet? Let's just define that because there's a specific definition. So it has to orbit a star, so simple. It has to be massive enough that its self-gravity results in a roughly spherical shape. So that's key. That kind of omits little things like comets and asteroids. And it has to have cleared its own orbital path. And so that means when it's going around a star, there's not a bunch of other stuff in the same kind of general orbiting, circle or ellipse. So for instance, Pluto hasn't really cleared its own orbital path in our solar system, so it's not a planet. It fulfills 1 and 2, but not 3. And so if you look at any stellar system, there's a whole bunch of stuff that orbits a star, but planets are distinct from each and all of these, and you can see the different, classifications here. Planets are their own thing, and you have to fulfill these 3 criterion here. So how does the stellar system form, or really the star form? It begins with the collapse of a gas cloud. And this slide is going to be very familiar if you remember the introduction to Milky Way formation, because the basic idea is pretty much the same. You have a cool, dense region. In this case, you have something like a nebula, where there's a lot of gas that's relatively cool and relatively dense. And so that overdense region then is going to collapse. And the particles that are inside this gas cloud, they're going to have some, random motion. And in all likelihood, there's going to be some net rotation. So if I add up all the leftward motion and I subtract all the rightward motion, then odds are it's not going to perfectly cancel. There's going to be some general rotation here. And as they collide, they're going to kind of homogenize. They're going to, begin to it's going to be easier basically to just follow the stream of rotating particles. And so in general, particles are going to begin to kind of rotate in the same direction. And so after some time, what's going to happen is your gas cloud then is going to collapse into a disk. And really there's going to be a substantial clump, a spherical clump at the core, but there's a disk basically because of this kind of collapsing that happens just due to all of these collisions. And so at the center of our disk, this is where our star is going to form. And then the planets themselves are going to condense from all of the stuff that's out in the disk that's not near the center. And we'll deal with the planet formation in the next lecture. And so for now, we'll just focus on the star formation part. So when does our gas cloud collapse? That's described by something called the Jeans criterion. So if we look at our cloud of gas, the energy in the cloud of gas can mostly be summarized in terms of the gravitational potential energy and the kinetic energy. So the potential energy, this is just the amount of energy you have stored for being at some height from a central object of mass, basically, is one way to think about it. So for instance, if you stand at the top of a bridge, you have a lot of potential energy. If you were to hop off that bridge, you would go speeding towards the Earth, and your potential energy is getting converted into kinetic energy. And the gas cloud has kind of the same thing. There's not a central massive object, but every molecule in the gas cloud is gravitationally attracting every other one. And there's some center of that, basically, and things are going to be collapsed towards that center. So the classic example for thinking about energy is a roller coaster, and what you have here is the roller coaster starts out at some height, it's going to be all potential energy. As it goes down the hill, that gets converted into kinetic energy and back. So our gas cloud has these two forms of energy. If the gravitational potential, if that can overpower the kinetic energy, then the gas cloud will collapse. Right? So you have gravity basically pulling inwards, but then all these gas molecules are kind of zipping around at some speed because of the temperature of the gas, and you need enough potential to overpower that zipping around of those gas molecules. So if it does overpower it, then it'll collapse. We're not going to work through the calculation of how you calculate the kinetic energy and the potential energy and equate the two. If you want to do that, take Astronomy 4201. If you do that, you'll find that a cloud of molecular hydrogen will collapse once its mass has met the so-called Jeans mass. And so for a cloud of molecular hydrogen, that's roughly 25 solar masses times the square root of the temperature of the gas cubed divided by the molecular density. So T here, this is the temperature in units of Kelvin, and N, this is the number density, so molecules per centimeter cubed. And if you take kind of typical conditions for a nebula where you have star formation, then the temperature is something like 10 Kelvin. Number densities can vary widely, but 1,000 molecules per centimeter cubed isn't out of the ordinary. And so if you plug that into this equation, these two will basically cancel, and you get that around 25 solar masses is when your gas cloud will roughly collapse. So obviously, depending on temperature and density, it may be a little more or a little less, but that's roughly what we're dealing with. Now, you might remember from an earlier lecture that the mass function, the initial mass function of stars is, there's not a whole lot of 25 solar mass stars being made. So if I take a plot of the sort of the mass distribution here, you'll see that almost none of the stars are being made with 25 solar masses. And so that seems to be inconsistent here, right? We're saying our gas cloud will collapse at 25 solar masses, but we have almost no stars there. Well, what happens is something called fragmentation, and this 25 solar mass cloud of gas will also then kind of break up into other little smaller spheres, and that's what gives you these much smaller mass stars that are typically more like, a little less than a solar mass. Now, there is an issue with the story I just told you, and if you were paying very close attention, you might have caught it. It's that we're converting potential energy to kinetic energy when we collapse, right? Just like the roller coaster that's pictured here. So as the cloud collapses, you get more kinetic energy, but that means that the temperature is increasing, right? Because temperature is really just a measure of the kinetic energy of your gas. So when we're collapsing, the cloud heats up. And why is that a problem? It's because our Jeans mass depended on the square root of the temperature cubed. So if you collapse, your temperature increases, but that means I now need more mass in the cloud in order to fulfill the Jeans criterion, in order to collapse. So then your kinetic energy will no longer be overpowered by the gravitational energy, the force of gravity. And so that's a problem, right? Stars wouldn't form in that case. So a key to star formation is you need cooling. This gas cloud has to cool in some way in order to form. And so what's the mechanism is basically that kinetic energy is converted into radiation, so into photons that can then stream out of the gas cloud, take that energy away, and it's free to cool down and then therefore to collapse more. So a common way to cool is molecules. So you can have carbon monoxide, or you can have molecular hydrogen, or depending on what's in the gas cloud, lots of stuff. So you can have a couple of molecules, they'll collide, and then that kinetic energy gets converted into some kind of excitation of your molecular system. So for instance, two molecules can collide, and that energy can then cause one of the molecules to start to vibrate. Okay, it'll have some extra energy now, and it's vibrating with that energy. Because this isn't the ground energy state, this molecule will eventually de-excite, in this case emitting a photon, and then it'll stop vibrating. It won't be vibrating like this anymore. You can also have molecules rotate. You can excite electrons in the atoms of the molecules. There's lots of different stuff. The main picture here, though, is you have things colliding, and the kinetic energy is converted into radiation. And the photons that escape will therefore have taken energy out of the gas cloud and cooled it. Another way is you can have dust. So there's a lot of dust in space, and by that we mean it's a conglomeration of a handful of molecules, anywhere from there up to something that's like, I don't know, a little less than a human hair thickness, or 1% of a hair thickness, something small, several microns. So this dust is also present, and these things can collide, and when they collide, that kinetic energy will be converted into heating the dust particles, and those can then cool by radiating thermally, just like you and I are radiating thermally. So you think of like a black body spectrum for this dust grain. So those are kind of our two ways to cool, and this is absolutely essential to star formation. You need this cooling. So let's, to conclude, look at what star formation looks like on the Hertzsprung-Russell diagram. So remember the HR diagram, we have luminosity versus the temperature, where the surface temperature increases as we go to the left here. So our gas cloud, what will happen is it's just going to free fall until you dissociate the molecular hydrogen, and then you no longer have any molecular cooling. So the collapse is going to then be much slower at that point. So once that's happened, then we call our object a protostar. So it's cooling relatively slowly, but there's no hydrogen being fused in the core yet. So it's not a full star, it's just a protostar. So the cooling time scale, how long it takes for our protostar to become a star, is the Kelvin-Helmholtz time scale. And so you're going to want to go back and review the Introduction to Stellar Equilibrium lecture, and you'll then see how to calculate that Kelvin-Helmholtz time scale. It's basically just saying, okay, I have a given luminosity. How long would it take for me to radiate away the gravitational potential energy if I was emitting light at that particular luminosity? And that's your Kelvin-Helmholtz time scale. And you can see from our diagram over here that the time to go from becoming a protostar to being somewhere on the main sequence where you're fusing hydrogen can be anywhere from on the order of 1 million to 100 million years. Something like that is kind of typical. Now, as your gas cloud is collapsing, it's getting hotter because we're converting, the potential energy to kinetic energy. But so you'd think that the surface would be heated up of this thing. But keep in mind that we're seeing less of a way into the star. The star is denser, right? So the optical depth is shallower. And to review this, go back and look at the stellar energy transport lecture. So the point I'm trying to make is that the surface temperature then is basically constant, okay? So though the surface is getting hotter, you can't see as deeply into the surface because it's denser. And so for the effective surface temperature for some distant viewer is going to be constant as the star is collapsing on the HR diagram. And yet the radius is decreasing because it's collapsing, so the luminosity is going to decrease. So that means that as your star goes from protostar to actual main sequence star, it's moving roughly vertically on the HR diagram. So the temperature is not changing much, and the luminosity is changing quite a bit, so it's moving vertically, and this is something known as the Hayashi track. And stars that are around a solar mass and less, this is most of their evolution on the HR diagram, is they're mostly following this vertical Hayashi track. Now, what's relevant for more massive stars, especially as you get later into the collapse, is that the collapse is extremely slow. And so your protostar is almost in hydrostatic equilibrium. Right? The outward pressure is almost balancing the inward force of gravity. And so that means your luminosity is just barely changing. And so instead, as this star collapses, it's basically just moving horizontally. So it's heating up, but the surface luminosity is barely changing, and this is known as a Henry track. Actually mathematically describing these it takes quite a bit of work, but you at least kind of know the the rough hand waving explanation for where star formation goes on our Hertzsprung-Russell diagram. And that is it for this Introduction to Star Formation for Astronomy 1000.